Mach's principle is talked about as an extraneous principle. It is not part of any standard theories of physics today. There's a reason for that, which when I first realized this, I was really amazed. Mach's principle implies that there is one universal frame, one universe. Because Mach's principle says effects of dynamics, centrifugal force and things like that, happens because of some interaction with the rest of the matter in the universe. Whatever that interaction is, since universe is one reference frame, accepting Mach's principle immediately implies accepting an absolute frame like aether and so on. But once you accept an absolute frame, the direct consequence is that propagation of light is Galilean. The relative velocity of light will depend on the velocity of the observer. So Mach's principle cannot be incorporated in current physics without breaking Einstein's theory, without throwing away Einstein's theory of relativity.
Welcome back to Demystify Sci, soon to be named something else. We are actually considering expanding our name to include more of the topics we explore on this show, which clearly reaches way beyond science and even mysticism. So we are playing with new ideas. So look forward to Demystify Sci having a new flavor to its name very soon. We're going to start rolling that out and trying out some ideas and discussing it with our patrons.
Suggestions are welcome.
Today on the show, we are exploring the underlying assumptions of relativity and some contradictory experimental evidence with respect to special relativities, so the invariance of the speed of light, this idea that the speed of light is the same for everybody, regardless of their motion. And today we have C.S. Unnikrishnan from the Defense Institute of Advanced Technology in India. He is a physics scholar who has worked on the LIGO projects, and he has come to some very startling realizations concerning the history of physics and the way that we have applied our foundational assumptions to the picture of how the universe works. And in particular, he's very concerned about this idea of descriptions, these empirically defined equations being mistaken for explanations, because there's a number of abstract postulates that are roped into them from the beginning. And of course, descriptions can be very, very deceptive, right? You can watch a magic show with David Copperfield and be absolutely convinced that the Statue of Liberty disappeared. It might look like that from every conceivable angle in the audience, but there's something else happening, and it's the job of the scientist to come up with hypotheses for what that something could be. And so we're exploring this issue in depth over the course of his conception of how this can be rescued by bringing in Mach's principle and really understanding that there's a lot of stuff in the universe that we can't see. It's really far away, but it does exert gravitational effects and mass, and those things should be applied to all of our fundamental understandings and interpretations of these bizarre relativistic experiments.
Absolutely. And if you like what we do, come over to patreon.com/demystifysci. You can help us brainstorm a new name. You can help us by supporting the podcast with just a couple dollars a month. And in return for that, we give you both of the episodes early, so you get them on Saturdays instead of having to wait until everybody else gets them. But you also get to join our patron chat, which is a Zoom call that we have every week where we get together and we talk about the larger, bigger questions that people are curious about. And it's pretty cool. We have maybe a consistent group of like 15 people that come, and there's probably another 5 or 6 that just hang out in the chat. And so it gives us a chance to actually connect with one another. So this is less of a isolating and atomized project.
One-way street.
Yes, it's less of a one-way street. So if you have a couple dollars to spare, come over to patreon.com. We would absolutely love to see you and get your support. And in the meantime, enjoy our conversation with Professor Unnikrishnan. We'll see you next time.
The scientific revolution starts now.
Demystify Sci podcast.
Let us see in the dark.
All right, so to kick this off into the science, I was hoping that I could read a little portion of one of the papers you sent us, and maybe we can springboard off that into what we're going to be talking about today, which is fundamentally a conversation about revisiting old experiments, revisiting tried and true theories, and considering their interpretation. There's a philosophical dimension of this, which is really interesting to us because, as we've been over and over on this show, empiricism really just shows you how a pattern unfolds. It doesn't necessarily give you an explanation of the cause of that pattern. And physics has been extraordinarily successful with detailing these patterns and equations and coming up with these, they call them theories, but they're really just these statements of how predictable events unfold at different places in the universe, at different scales. And one of the most successful theories, kind of the bedrock of modern physics, is Einstein's relativity. And what we're going to be talking about today is the strange implications of relativity and how they might be just misunderstandings. So I'm going to read a little piece of this paper. I'm going to just skip through a couple excerpts. People should go read it themselves. It's called A New Gravitational Paradigm for Relativity and Dynamics and Its Philosophical Scope. And this is from Journal of Physics conference series. And so the piece that I wanted to share to kick this off, it goes like this. Einstein's theories are interpreted not only as the theories of relativity and gravity, but also as the theories of space and time themselves. And then skipping forward, while these are factually, let's say spatial intervals between material particles and the duration marked by material clocks, the essential and crucial role of the material markers is dropped at the level of abstraction without logical rigor. And then it goes on, the unobservable space-time is elevated to a full-fledged dynamical entity in the general theory of relativity. So that there's a creation of this abstraction being turned into a physical substance. And then to close out the little excerpt, you say, in real physical terms, all observable experiences of gravity are limited to matter affecting spatial separation between material particles and the rate of material clocks. So there's this divergence from material representations of reality and theoretical abstractions. There's some confusion, some conflation of abstractions with material reality that's at the core of this discussion. And so before we get into all of the disagreements with the interpretation, maybe you can just comment on why it matters. Who cares if people have made these mistakes treating these abstractions as physical substances and so forth? Why does it matter?
Because the math works.
Okay. Yeah, the math works. That is true. The point is, it is not only we observe various phenomena. So one doesn't have to really explain the phenomena to observe the phenomena and even describe it in ordinary language, or even convert those phenomena into technologies. You don't have to really understand it theoretically completely. Yet, it's our urge that we want to understand it more deeply, closely, and we form theories. In the sense, we try to connect up various phenomena and describe them on the basis of a few fundamental concepts. So space and time are two fundamental concepts which we start with for describing dynamics, some object moving. Of course, it's always the matter object which is moving, because that is all what we can experience. But to describe that motion, we need some reference that a particle moved from one position to other position. And how do you talk about these positions in space? Space is our experience, in the sense we live in space, and time is something which we experience as evolution of ourselves evolution of our environment and so on, which we call time. So when we say time passes, what we mean is something evolves,
Something changed.
something changes. So space and time has two essential concepts that was always needed to describe motion. Now, when I talk about motion, movements, it is just not physical movement of some particle in space. It's also used as a general term for evolution, change. Now, so space and time. Now, if you imagine removing
Before you
all,
go on, can I ask you a quick question? How do you conceptualize motion without, evolution or change without some particle being relocated?
you cannot. In fact, that is a point. Suppose you imagine a situation where there is no matter at all, nothing
Right.
material. Now, you may be able to imagine space without matter. At least some people will be able to
In a
imagine
coordinate sense or something like that. In a
something.
coordinate.
When you say imagine empty space, people may be able to imagine empty space, but you will not be able to imagine time without any matter. There should be at least one particle which is evolving, which is moving. There has to be some particle, some matter in which we can experience, which is changing. Either it is changing its position, or it's changing some property like its temperature or something. Something should change.
Would it be fair to say that you need two particles because you have to compare that motion to some standard of reference?
Exactly. So therefore, one of the motions, when you refer to time, every instance, when you refer to time, what you are doing is to compare one kind of motion with another kind of motion. One of them you use as a standard, something which is simpler. Maybe it's a periodic motion of something, which you take as a standard. Otherwise, you are always comparing a change with another change. When you say, I have a clock, I have time. So the sense of time, if you really think about it, without matter, it has no meaning at all. So now, given this context, when you say space and time are physical entities, without referring to matter at all, there is really a conceptual problem. There is a philosophical problem.
Mm-hmm.
It is not rigorous enough. It is not sufficient. So if you go really deep there, already you are stuck with these primitive concepts. They are metaphysical concepts, actually. They are not physical. Not quite physical, I would say.
Can I just pause you there for a second? When did people begin to be concerned with this? Was this something that people realized as soon as relativity was born? Was this something that was on the tips of people's tongues, or has this kind of really been underground this whole time?
This
No,
meaning
This lack of
reification?
the lack of physical reference points.
This is already in Newton's Principia.
Okay.
Because Newton wanted to axiomatize everything which he was talking about. So he wanted to talk about space, time, though he started by saying that he didn't want to define, because these are sort of obvious concepts. He still tried to talk about them, as define them. And then because he had to describe movement of objects, dynamics in space and time. And then he had to say something about what is time and what is space. So he started by defining space, and in the beginning of Principia itself, he makes these definitions. However, he immediately got stuck, because he had to define. Once he defined what he called absolute time and absolute space, without reference to anything at all. That's what he meant by absolute. Without taking support of matter and various other concepts, purely primitive, pristine concepts. He defined space and time, but he couldn't point to what is space, what is time.
So
How
he
do you
defined them
distinguish?
quantitatively or something. Is that what you mean by definition?
Yeah, he just defined it sort of lyrically. You can always give a definition in terms of words, but how do you point to some object? How do you recognize what is space, what is time? He said you cannot, because instead of the absolute space and absolute time, in their place we use, in practical terms, we use what is called relative space and relative time. And relative space is when you make markers in space and define a motion with respect to those markers. And markers are material references. Similarly, time, relative time, some change is happening. You take that as some reference and describe another change.
So
it
clocks.
was, yeah. So it was Newton who realized the necessity of distinguishing between space and time as metaphysical primitives, and also provide ways of identifying what could be used as relative space and relative time. So everything he wrote it systematically in Principia, because he also had to talk about certain phenomena which we see, like centrifugal force. This you discussed in an earlier podcast with Assis, for example.
Mm-hmm.
So he wanted to give, since he defined absolute space and absolute time, he also tried to give a proof for the existence of what he called as the absolute space. And he said, absolute space can be, the existence of reality of absolute space can be seen in phenomena like centrifugal force. When a mass of liquid in a bucket, if it's rotating, the fact that its surface becomes curved. This kind of a thing happens only because the body of water is rotating with respect to absolute space, according to him. Of course, this was criticized much later by Ernst Mach, 200 years later, where he said what Newton claimed has no basis, because when you say a body of water rotates, it could be just rotating with respect to all the matter in the universe and not with respect to absolute space. So it could be an interaction which causes this curvature of the surface of water, real interaction with the rest of the matter, and not some abstract, unobservable entity like absolute space and so on. So that
Which is a small difference, right? It's a very tiny difference, but it's a really important difference. I feel like Newton was observing this phenomenon and trying to make sense of it, but he stopped thinking about interactions with matter, and that's where things maybe first go off the rails a little bit. But can you address the question I put earlier, that were people upset about this when this happened? Were there philosophers that were coming out and saying, no, this can't be?
I mean, it's very Platonic, the idea of absolute space and absolute time.
Yes, it's an old concept. It's a very old concept. Absolute space without matter, something which can hold. There is a book by Max Jammer on space, and a preface is written by Einstein, where again these questions are discussed. What is space and what is time? But of course, these are much later. But after Newton, I think there is some discussion by Bishop Berkeley on this issue. But otherwise, a serious discussion and a serious proposal, an alternative to what Newton was saying, that happened only with Ernst Mach.
So people were
Later,
upset, but they didn't have an alternative. They weren't totally sure how to
no.
interactively link it.
I'm not
Yeah,
even sure that people were upset at the time of Newton.
No, that's right. Yeah, there was nothing to be upset about it. I mean, it was acceptable. In fact,
Like it worked, and he had mathematically created. I've always seen Newton as the guy who is able to put mathematics in motion, and people are so tickled by that they're like,
And
whatever assumptions this guy had to make to do this, fine, because this
also,
works, and now we can predict things and design.
Also, I don't think people felt very strange to think of space as some entity which was there as some absolute abstract thing, even without matter.
Because there's a long philosophical tradition of the void.
Yes.
And the void as this concept seems very similar to absolute space, and it seems like a logical, not a huge leap to say, well, okay, if there is void that is unchanging, then there also must be some ticking pendulum somewhere that will never change, that everything happens on the backdrop of.
For example, you look at serious physicists today. Today, most of the physicists, practicing physicists, are willing to accept the concept of space without matter, time without matter. So I think people get upset the other way. If you say these things happen because of some interaction, people get, what interaction?
We have an article hanging on our wall by Lee Cronin and Sarah Walker that was in some science magazine the other day, where they argue that time is an object. Right, and so I think that you're right, that the greatest problem has always arisen when somebody shows up and is like, hold on. Can we get back to the material at hand here?
I mean, was Bergson really the first critic? You talk about Henri Bergson a lot in your work, and was that the first outspoken critic of this misplaced concreteness?
No, Bergson comes into picture from another angle. We'll come to that. But I want to make one more point on this, why people were not upset with absolute space. See, when you look up into the sky, you see matter, stars, Milky Way. But if you look at the amount of matter you see in terms of stars and one galaxy, that is really not enough to fill the whole space you can imagine. Okay, in that sense, one always thought of largely empty space filled with a few stars and so on. We didn't know the extent of this universe, how much matter it consisted of. All that came in this last century. Before that, all this, we had a solar system and a little bit of stars everywhere, but compared to empty space, this is a very minuscule amount of matter.
I believe they thought our galaxy was the extent of the universe all the way up into the 20th, almost the mid-20th, 20th century.
That's why even when Ernst Mach talked about some interaction which could be responsible for things like phenomena like centrifugal acceleration, he could not suggest it could be the gravity of this matter, because once you say it is gravity, then you can always calculate using Newton's theory how much gravity. If you calculate gravity with only Milky Way or one or two Milky Way like galaxies, you get a very, very small amount of gravity, which is not enough to explain anything which you see. So all this realization could not have happened even if you had the idea before we knew about this universe.
I think now we can at least observe by statistical sampling something like trillions of galaxies.
Yes. Now we have a rough idea of our vast universe, how much matter is there. and it has real serious consequences to our current theories.
And you make this point in the paper that you shared with us, which is that the theories that are foundational for physics were completed before we ever had this information. And the information wasn't even theorized. It wasn't that the theories were put together with the idea that there was this vast universe that was filled with so much material. They were constructed in the sense of, okay, well, we have very little material.
And we stuck with those theories.
And they haven't been revised. And I think that that's the core of your argument, which is that, okay,
Yes.
so we have these theories that were constructed with a limited base of knowledge. And we have accepted them because they're mathematically very beautiful, and I'm
Yes.
sure that there's cultural effects in there as well. But now we have come out the other side, and we have so much more information, and we have to go back and we have to reevaluate Einstein's theories to see if the core postulates hold, knowing everything that we know and everything that we've accumulated in the times really since Newton.
Yes. So right here, one can make a point which we can come back to again and again. When you say, let's look at the concept of absolute space of Newton's. Now, when you say absolute space, one is talking about one space, one entity. There is only one absolute space you will talk about. When you say absolute time, you are talking about one universal time. Conceptually, that's what you mean by that. There is one reference time with relative to which all other times are measured. There is one space, one holding space in which everything is arranged in various locations and so on. Now, when you talk about a universe, there's only one universe. When we say universe, it is one frame which we are talking about. Then everything else, every other motion, every other position, every thing which is happening, evolving in time, all this will have to be referred to this, what the dynamics of one universe. Then that universe provides reference for dynamics. Now, there is a very intimate connection between this kind of a concept of one absolute reference and things like the propagation of light. If you remember, before Einstein's theory came up, we had a theory of relativity, which was developed by Lorentz and Poincaré. And this theory had as its background what they called absolute ether. Absolute ether was a hypothetical medium which was postulated so that the waves of light could propagate in that medium. It is like air for propagation of sound. So people believed that there should be some medium for the propagation of transverse waves, because that's our experience. All transverse waves which you know, all kinds of waves we know of, they all propagate in some medium. So a medium was postulated even before the theories of relativity came. There is one medium, it's an all-pervading medium which people had in mind. And in that medium, light propagated like sound propagates in air. It has some particular velocity decided by the properties of that medium. Now, if you are an observer who is moving relative to that medium, you will measure a different velocity for the same light. Light is propagating in the medium at one velocity. You move in that medium, then relative to that observer, light will move faster or slower depending on the direction of the movement. So that is a common sense view. So the old relativity of Lorentz and Poincaré had the velocity of light depending on the motion of the observer. It was not an invariant velocity. All this was changed by Einstein's postulate of invariant velocity of light. He postulated that the relative velocity of light is a constant, no matter whether the observer is moving towards a ray of light or moving away from a ray of light. If you measure the velocity, it's an invariant constant. And so he had a different theory of relativity, which was different from the theory of Lorentz and Poincaré. However, the mathematics which is used to describe that theory of relativity was exactly the same, Lorentz transformations. So it's very interesting that at some stage in the development of physics, let's say 1900, we had two theories of relativity. Both were acceptable theories of relativity because both agreed with every experimental observations we had in those days. From Michaelson Morley experiment to later things, both theories agreed with empirically with phenomena which we could see in the laboratory. However, the basic postulates which go into the two theories were entirely different. In one theory, light traveled with a variable velocity. However, there were new phenomena, relativity, like length contraction, time dilation, so on. Those new phenomena, coupled with the propagation of light, somehow explained what you can see in the laboratory. In Einstein's theory, very similar phenomena were proposed because he used the same mathematics. However, the way Einstein set up this, how the observability of this phenomena, he arranged such that even with the invariant velocity of light, he could explain the same phenomena. Now, sociologically, this is where some amount of sociology comes. Sociologically, Einstein's theory was gained prominence very soon. Most of the physicists, including Lorentz, sort of agreed with what Einstein said. Lorentz said, what we were trying to explain, Einstein just postulated and went ahead. So, at some stage, Einstein's theory gained prominence and it got accepted. Though there is not even a single experiment, even today, there is not even a single experiment which can prove that a relative velocity of light is a invariant constant. Experiments are consistent with that postulate, but there is no experiment which can prove this postulate directly.
Why is that?
There are subtle reasons for that. There are subtle reasons. One would imagine that if you measure the velocity of a propagating entity, you can settle the question whether the relative velocity is a constant or variable. It sounds simple enough. For example, if you want to measure the relative velocity of sound, all you need is two microphones set apart by a meter or so on a frame. Then you have a source of sound somewhere. You make the sound, you measure the duration to pass between two microphones. So you have a duration, you have a distance fixed by the two microphones. Then you take a ratio, you get a velocity. Then you can move the whole thing and you can measure the same velocity relative to a moving reference frame. Therefore, it is very easy to decide whether the relative velocity of sound is variable or a constant. And when you do this experiment, you will see that the relative velocity of sound do it does depend on the velocity of the reference frame.
This is just the Doppler effect, right? This is how sound.
Doppler effect is related, but Doppler effect is on the pitch, on the frequency of sound.
I see.
But the velocity is just a ratio between the distance traveled and the duration taken for traveling that distance.
And the Doppler shift happens when you have a stationary detector and then the sound sources are moving relative to it. But the experiment that you're describing, the microphones and the sound source are all moving together as one unit?
Okay, that's an interesting question because, there is one aspect which is not very clearly explained even in textbooks. Whether you take sound or light or even waves on water surface, the velocity of these waves does not depend on the velocity of the source. That is,
it's entirely defined by the medium.
It is, that's exactly. It depends only on the properties of the medium. And this is true for light as well as sound. The velocity does not depend on
just to make sure that we set this absolutely clear, the Doppler thing is just that you're encountering more peaks on the wave because which is different than the actual motion of the waves.
Yeah. Whereas the real question in relativity is whether the relative velocity, whether it depends on the motion of the observer, the reference frame, not the source. Okay. Now, what is interesting is, in the
which
case
would be
of
entirely unique in the universe, right? That would be entirely unique as far as waves propagation is concerned.
I didn't understand that question.
Well, that would be a very exceptional physical phenomenon if that was true, because it doesn't seem to play out that way in any other wave systems that we're aware of.
Right. That is, if there is a medium, it's obvious that the relative velocity will depend also on the motion of the observer. It is very clear that if there is only one frame, if there is an absolute frame, one could identify whether it is ether or something similar, then the relative velocity will depend on the velocity of the observer. So
hold on 1 second. I'm really sorry, but weren't we just saying that in the case of sound that it only depends on the medium itself, but not the observer?
No, it doesn't depend on the velocity motion of the source, but it does depend on the velocity of the observer. So if you move these two microphones towards the source or away from the source, the duration taken to travel from one microphone to the other will depend on the velocity of the microphone, which is obvious because the sound reaches the first microphone at some time, some instant. Then by the time sound reaches the next one, that microphone has moved away.
I see.
Therefore, obviously, it has to take more time, more duration. Therefore, relative to the microphones, you have to say the velocity is less. Relative to somebody watching this experiment, what happened was, microphone was moving away. So it took more duration. But if you are sitting in the frame of the microphone, if you are moving with the microphone, then it is as if the relative velocity has reduced to reach from one microphone to other. So when you say relative velocity, it's always a comparison between two observers. One observer who is watching outside the frame, another observer who is sitting with the frame.
Got it.
Like we are sitting on the earth, but the earth is moving at a very, very large velocity, which we don't realize about. It's not only the velocity in its orbit around the sun, but it's moving through the universe at about 350, 370 kilometers per second. We don't realize that. So the question is, if a light ray is coming from outer space into our rooms, it touches one window at a particular instant. By the time it reaches the next window, the room itself has moved away a long distance. Now the question is, even with that kind of a phenomenon, how can it happen that the relative velocity of light be a constant? How can you postulate such a very strange uh, conclusion? That is why it is really a strange postulate. In fact, I have something. Charles Nordman, he was a radio astronomer. He was a friend of Einstein. He was an admirer of Einstein. He wrote some report on Einstein's visit to Paris in 1922. A very well-written short report on the visit. And that time, he mentioned this strange postulate of the constancy of the relative velocity of light. And he wrote it this way. There is hardly, he said, however, there is still something infinitely troubling in the Einsteinian system. This system is admirably coherent, but it rests on a particular conception of the propagation of light. How are we to imagine that the propagation of a ray of light could be identical for an observer who flies away from it and for an observer who rushes to meet it? If this is possible, it is in any case inconceivable to our customary mentality. And no matter how hard we try, we cannot make the mechanism and the nature of that propagation intelligible. It must be confessed that here lies a mystery which eludes us. The whole Einsteinian synthesis, as coherent as it is, rests on a mystery exactly like revealed religions. That's what he said. And that is true. It's a very strange concept. But once you postulate that invariance of the relative velocity, all results of relativity theory follows from that. Lorentz transformation, everything follows from just that single postulate. That is what Einstein did. And people accepted it, even though it was a strange concept. People accepted it because it gave the full theory. When Lorentz and Poincaré created the theory of relativity, it was a step-by-step progression where people had to work out each detail because it was based on this another strange concept called aether, which we cannot see, we cannot feel, we cannot get any evidence for it. But it was also postulated. And people thought any day Einstein's postulate is less evil. I mean, than accepting something like a ether. So
why do you think that is? I mean, they both, I understand an unobservable, hypothetical, unobservable, this postulate of the ether is difficult to stomach, but some exceptionalism to physics as we understand it seems even worse to me. Why do you...
There is one reason. There is one reason, and I think it's an important and genuine reason. If you look at the theory of Lorentz and Poincaré, it is based on electrodynamics. Either was a medium which was meant to support electrodynamics phenomena, all phenomena in electrodynamics. And Lorentz was trying to derive every result of relativity as an electromagnetic phenomena. Because matter, it was already known by that time that matter consists of atoms and probably electrons. And there's electrical forces holding matter together. Therefore, he was trying to derive everything in relativity using electrodynamical phenomena. In Einstein's theory, this cage of electrodynamics is broken. It's a more general theory. Having postulated the invariance of the relative velocity of light, then a theory follows from this postulate. That theory is supposed to be applicable to all phenomena in physics.
So it's
not
the
only
temptation of
electrodynamics.
the temptation of the universalization, this
Yes,
holy
exactly.
grail of physics that I can talk about
Right.
everything all at once.
Yes. So therefore, you would agree that all of us would agree if we are supposed to pick one of these theories, we would say we will prefer the more universal theory which is applicable to mechanics, electrodynamics, optics, everything else. That is what happened. However, we should realize that the postulate was not experimentally verified. It was unverifiable because of certain reasons. Now, one reason I can immediately tell you, when you say a particular velocity, when you think of the concept of velocity, it is a statement of the duration taken from for moving from a point to another point. So there is a starting point, there is a final point. Now you need two clocks, one clock at the starting point and one clock at the finishing point to measure a duration. So you can fix a distance by pre-measuring that distance. You can say this is 1 meter, but the duration is measured with only two clocks, not with one clock. So if you are an observer who is at position A, first point, that observer has no access to the clock at B, position B. At position B, there is another observer. So there is a problem of synchronization of two clocks. How are you to make sure that these clocks read exactly the same time? For measuring the velocity of sound, it doesn't matter because velocity of sound is a small quantity. We can synchronize clocks with a accuracy much. The point is there are things which move faster than sound. So those things can be used to synchronize these two clocks. But there is nothing which moves faster than light. Okay. So to synchronize two clocks for measuring the velocity of light is not only a technical problem, it's a conceptual problem. How can we synchronize these two clocks? If you use light for synchronizing two clocks, then it becomes a circular argument. You are trying to measure the velocity of light and you are using the same light to synchronize two clocks. So that is a circular argument. You cannot do that. If you synchronize two clocks at the same position and move one of those clocks to the second position, you need a theory of moving clocks. You have to make sure that nothing happens to this clock while moving. But theory of relativity is also about what happens to moving clocks. So you see, conceptually, there's a difficulty of synchronizing two clocks when you want to measure the relative velocity of light. Therefore, all traditional experiments in relativity are what are called two-way experiments. You send light, get it back by reflecting, Michaelson Morley experiment and so on. Now, when you are in a moving frame, let's say you are in a moving vehicle, a moving train, or moving earth, and light propagates in one way, you don't know what its relative velocity is. But when light propagates the opposite way, whatever effects which happens because the velocity varies with the motion of the observer, that effect gets cancelled out. Because one way is along the motion of the frame, other way it is opposite the motion of the frame. So this cancellation happens to a large extent, because of which you cannot determine whether the propagation of light is with a variable velocity or with a constant velocity with any of these two-way experiments. But
And
those
it
are the
would
only
be the
experiments.
same thing if we did our microphone experiment and we reflected that sound source in the moving reference frame.
There is it's almost same, but there is a subtle difference. There is a subtle difference. So when I say in the two-way propagation, it cancels out. It does not cancel out entirely. There's a small second-order effects, something which depends on the square of the velocity. That is in one-way propagation. If you could measure, for example, when you do this experiment with sound, you will see that with microphones, as you move the microphone, the velocity, relative velocity changes, and that change is proportional to the velocity of the observer. In a two-way experiment, that proportionality does not anymore survive. It cancels out, but there is a residual effect which depends on the square of the velocity, next order, which is a much smaller quantity. What I mean is, when I say first order, it's a ratio between the velocity of the observer and the velocity of the light or sound. For example, velocity of sound is 300 meter per second, let's say 300 meter. And the microphones are moving at 1 meter per second. So 1 by 300 is the velocity of the observer divided by the velocity of sound, 1 by 300. That's a kind of signal you can get in an experiment when you do this experiment in a laboratory. The relative strength of the signal. So if it is if the microphones are moving by 1 meter per second, you get 1 by 300. If it moves by 2 meters per second, you get 2 by 300 and so on. Proportional. However, in a two-way experiment, if you reflected sound like a Michaelson Morley experiment, you get V square by C square, second order. So 1 by 300 square, which is much less, which is 1 by 10 to the power of 5. Much smaller. So, but there is a signal. You can measure in fact, that is what Michaelson and Morley were trying to measure. The second order signal, something which depends on the square of the V by C ratio, which is a very, very small signal. Because Michaelson and Morley were not trying to measure the relative velocity of sound. They were trying to measure the motion of the earth relative to the absolute ether. They were trying to detect the motion of the earth relative to absolute ether. So for that detection, they realized if light goes and comes back, you still have a small signal in which there is a signature of the velocity of the earth through the ether. Though it is a small signal, you can measure it. That's what Michaelson attempted.
Can I ask you just from a conceptual standpoint to help me understand why there's a residual in a two-way experiment versus a one-way?
Yes.
What is the cause of that? I'm having trouble understanding why that even happens. Not necessarily the math of it, but why is that? Why is there a reason?
That's a reason. Yeah, I can just sort of try to say it, and you can try to imagine what happened.
Yeah, let's see what we can do.
So the time taken. So I have a pulse of light which goes from point A to point B. Now the separation between point A and point B, let's say call it L, distance of 1 meter or L meters. Okay. Or let's fix it at 1 meter. Now the time taken, duration to pass this 1 meter is given by 1 meter divided by the velocity. Length divided by velocity is the duration. Now, suppose the relative velocity depends on the velocity of the observer. So if you are chasing, if the observer is moving in the same direction as a light propagation, the relative velocity will be less, c minus v. So in one direction, c minus v is a relative velocity. In the opposite direction, it is c plus v. So duration taken in one direction is 1 meter divided by c minus v. Duration taken in the other way, it is 1 divided by c plus v. Okay. Now total duration is 1 divided by c minus v plus 1 divided by c plus v. So this, because of c plus v and c minus v happens in the denominator and not in the numerator, they don't cancel out completely. What you get is 1 minus v square by c square. That factor will come. In fact, this factor is very important in relativity. 1 minus v square by c square.
I guess for me, I think like conceptually, it means that since this whole package is moving, it never really fully catches up to itself. There's some loss to this motion when you're moving with it. It seems like there's just a loss. It's almost like, I'm not sure how I can better conceptualize it than that.
I mean, I think that it ultimately the mathematics helps conceptualize it because you have this relationship where when you're moving, the speed has to take into account your motion in the same direction, and so that's c minus v. And then when it's bouncing back in the other direction, it also has to take into account your motion, which is c plus v. And when you mathematically try to combine those two fractions, you end up with this square second order relationship.
So the point is, it is a fraction. That is, if the c plus v and c minus v, if they are in the numerator, when you add up, the v will cancel out completely. But here we are talking about durations. Duration for the propagation. So it is length divided by the velocity. So c plus v and c minus v are in the denominator, not in the numerator. Therefore, when you add these two things together, there's a small residual which depends on v square by c square. And that was the logic what Michaelson used to design his experiment. He said it is difficult to measure the one-way propagation, but the two-way propagation is easy to measure because I can bring back the light to the location where I am. And though the signal is very small, I have this very nice technique of interferometry. He invented fine interferometry. I will use interference of light to measure this. And he set up the experiment. That's how, but what happened in the experiment? He did not see any signal. Though he had the sensitivity to see the v square by c square signal. See, if you look at the numbers here, the velocity v is the velocity of the earth through ether. And they assume that that velocity is the same as the velocity of the earth in the orbit around the sun, which is 30 kilometers per second. The velocity of light is 300,000 kilometers per second. The ratio v by c is 1 part in 10 to the 4, 1 part in 10,000. Square of that is 10 part in billion. So it was a small signal, but still it's a signal which has a signature of that velocity. If the velocity is changing, that one will be able to measure it using Michelson's interferometric techniques.
Can I ask you a question about interferometers before we move on? Which is, aren't we looking at some sort of phase shift of the wave in interferometers? Yes. And we're back calculating the velocity change as a result. Is that more like a Doppler type situation though?
It is not Doppler because the source, the interferometer, the observer, everybody is sitting on the same frame as in the laboratory. Doppler effects will happen only when there is a relative motion between the source and the detector.
Got it. So it's like in our case where the microphones are moving together, essentially.
Yeah, everything is moving together. But so when Michelson did the interference, it is measuring the duration. Since light is supposed to be a wave, if the duration taken for one-way propagation and then the reverse propagation, the total duration is what Michelson was trying to measure here. If that total duration depends on the velocity of the Earth through the ether, if that velocity changes, increases or decreases, then the number of oscillations of light in a particular distance also will change. Because when you say a phase of a wave, how many oscillations of a wave, it is just the frequency of that wave, which is a fixed quantity, multiplied by duration. So interference technique can be used to measure durations very accurately. That was a basic idea. And here we are trying to measure a duration. Duration for light to go to a distance and come back to the same position. What is the duration? Does this duration depend on the velocity of the Earth when it goes around the sun? And they found that they were not able to measure the variations in this duration, even though the interferometer could be rotated in space, so the relative velocity is changing. They know that they could change the relative velocity conceptually. However, the signal did not show any of this. So they could not detect the presence of ether. They could not detect the motion of the Earth through the ether.
And by ether, we're thinking of this static backdrop type ether, right? That's not really connected necessarily. It doesn't move around with things. It's just there.
Nothing. In fact, it has the property that it is not movable at all. It's stationary. They called it stationary ether.
Mm-hmm.
Okay, that word was used. Stationary was the word which is used to describe it. So the concept was there is an absolute all-pervading medium which is absolutely still, and Earth and everything else is moving through that. But they could not detect it, and they had to explain why they could not detect it. And Lorentz invented this phenomenon called length contraction.
Mm.
He said, okay, light is propagating with a variable velocity. Duration is actually changing, but I cannot see it because interferometer itself, when it moves through the ether, its length reduces a little bit. And that reduction in length also involves this ratio 1 minus v square by c square. So the two can cancel out. Okay, it is more subtle than this. It is actually square root of 1 minus v square by c square for length contraction. There is a similar effect on time dilation. Again, another 1 square root. So this 2 square root of 1 minus v square by c square multiplied together gives 1 minus v square by c square. So Lorentz could explain everything. So he said light is propagating in the same way with a variable velocity, but there are new phenomena, length contraction and time dilation. So all the three together conspire to keep this medium called ether invisible. That was Lorentz's theory. Einstein said, okay, this is all superfluous, extraneous things. We don't need all this ether. All we need is single postulate. Postulate that the relative velocity of light does not depend on the velocity of the observer.
So if they had designed the Michaelson Morley experiment not to measure relative to the ether, but to move the detector as the experiment is run? Would they have
You mean the
got-
source or something?
Well, the source and the detect, like the detect. So, assuming that so you have, let's say, an interferometer path, which you have point A and point B, and the light is emitted at point A, but then the detector begins to move from point A towards point B, and it's reflected at point B and comes back to the detector. Would they have gotten a different result? Would they have been able to see this change?
No, no. See, earlier I said all this does not depend on the velocity of the source. Velocity of the source is irrelevant.
But if
All
the
what
source and the detector are the same.
if the source and the
Well, because like imagine that there's a single pulse of light, like a single photon gets put into the system. So the let's say even the source and the detector aren't the same thing, but they start at the same place. Right.
the result will be exactly the same. What Michaelson and Morley got, this result is sort of a universal result. That will not change by changing the kind of source or any of the configurational changes. It will not. The point is the explanation that light is propagating with a variable velocity, but there are these new phenomena, physical phenomena, length contraction and time dilation, that works in all circumstances. You cannot say that this explanation is incorrect for any experiment. Only thing is you cannot distinguish this explanation from Einstein's explanation that no, that is not the reason. The relative velocity of light is an invariant. So these are two different explanations. You cannot distinguish with an two-way experiment. You cannot determine which explanation is right. So you need a one-way experiment. But one-way experiment, there are conceptual problems because you don't know how to synchronize these two clocks. So one had to invent a method. One had to invent a method where the synchronization problem had to be solved. Somehow solve it. You have the clocks had to be separated in space because light has to travel some distance. But somehow you have to synchronize clocks at A and clock at B. And what I could do, there are some people who attempted this in the history of physics. But all those attempts were using what is called a circular rotating experiment.
This is
For
the
example,
Sagnac experiment.
Yes. So when George Sagnac did this experiment in 1913, he did this specifically to show that, in fact, the ether exists or some absolute frame exists. So he had point A, light starts propagating from point A, but it comes back to point A. So point A and point B are identified. So light has to travel for a distance to get from point A to point B, but it's a looped path. That was his logic. In that experiment, he argued, so by the time light goes and comes back here, the point B moves a little bit, just like in a linear system, when light starts from point A to reach point B, by the time it reaches point B, the point B has moved a little bit. Therefore, the relative velocity or the duration is different. Here, a rotating apparatus, when the light goes in this loop path, the point B has moved, but now there is no burden of synchronizing point A and point B because they are together. It is as if one is using the same clock at A and B. Okay, but then the result was, in some sense, shocking, because it showed that indeed the relative velocity of light depends on the velocity of the observing frame, reference frame. However, by 1913, Einstein's theory had been already accepted by most of the physics community. Though there were some objections, still, some people were not very convinced, but there were very powerful, prominent physicists of that time, Max Planck, Lorentz, people like that. They had accepted Einstein's theory as the most plausible theory of relativity. And nobody questioned when Sanak's experiment came, results came, people tried to evade it instead of discussing it. That's what happened in history.
Yikes.
In fact,
who were the...
Oh, sorry. I was going to say, what was the readout of Sanyak's experiment? Was it a phase shift of the light?
yes, it's exactly same. In fact, whatever Michaelson was trying to measure, it's every time you do a interferometry experiment, a measurement with the interferometer, a change in duration is measured as a phase shift, and the phase shift is measured as a shift of the fringes, which you see. But this pattern of the periodic pattern of fringes, bright and dark patterns. So it shifts a little bit, and that is interpreted as a change in the duration of propagation, and that is how it is measured. And in Sanak's experiment also, that is what is measured. But Sanak experiment, if you look at, it's a one-way experiment. Light propagates in the same direction throughout, because the synchronization problem is not there anymore.
Mm-hmm.
Therefore, the signal is proportional to V by C, not V square by C square. So it's a much easier experiment to do, because signal is very large compared to Michaelson Morley experiment. So what happened in the history was, Sanak's experiment was not, it didn't get the attention which it deserved. But there is something very strange here in the history. The same idea, whatever Sanak had as an idea, Michelson had the same idea in about 1904. And he wrote a paper even before Einstein's theory came up. That was in 1905, Einstein's theory. Michelson wrote a paper in 1904 saying the following. Okay, in the earlier experiment where the two-way propagation of light was studied, the presence of the hypothetical ether was not found in the experiment. However, if a different kind of experiment is done, in which light travels only in one direction and comes back to the starting point, in that kind of an interferometer, I propose to measure the presence of ether. So he wanted to do an experiment in almost the same design as the Sanak experiment. But Michelson's interest was in detecting the motion of the earth relative to ether. So what he said was, he could not detect the linear motion of the earth through the ether, but he can measure the rotational motion, the spinning motion of the earth in the ether using a different design of an interferometer. But the kind of interferometer he had in mind had to be very large to measure the rotation of the earth. See, when Sanak did his experiment, he did it in a rotating frame in the laboratory. It was a tabletop experiment where the frame was rotated manually on a table. Michelson's interest was in detecting the rotation of the earth itself relative to ether. And since this earth rotation is at a very small rate, it takes 24 hours for one full rotation. The interferometer had to be very large in size to detect it. But he did this experiment in 1925. It is called Michelson-Gale experiment. He did it with a person called Gale. It was published in Astrophysical Journal in 2 papers. One paper was about the experiment. It was a kilometer-size interferometer, much like today's gravitational wave detectors and so on. And another paper was about the theory of this experiment, in which he stated that he detected the rotational motion of the Earth relative to aether. In 1925, I wrote that paper. So even in 1925, Michelson was a believer in stationary aether. He was a believer. He had repeatedly said that also. He sort of leaned towards the concept of aether. So he was convinced that there is an absolute frame. However, as I said, Einstein's theory was so prominent by that time, especially after 1919, after the eclipse, solar eclipse, the general theory of relativity, all that came together. And Einstein's theory was unshakable. The faith in Einstein's theory was unshakable, which continues to this day. But however, it's a fact that all these experiments are there in history. These are results which are there, which will not go away. And people said, so the objection to Sanac experiment was that, okay, it's a rotating reference frame, which is not equal to a linearly moving reference frame. In physics, there is a distinction made between what is called inertial motion and non-inertial motion. Inertial motion is when you move linearly on a straight line at a constant velocity. Inertial motion, you cannot distinguish, you cannot recognize, you cannot distinguish inertial motion from a state of rest. For example, we would say we are in inertial motion with the Earth now. We don't know Earth is moving at hundreds of kilometers per second because we are almost in inertial motion. So inertial motion cannot be distinguished from a state of rest. It is called principle of relativity. What is called principle of relativity is just this statement that you cannot distinguish inertial motion at any velocity from just a state of rest. It was stated by Galileo. And that's a fundamental principle of physics. So people try to distinguish between inertial motion and this non-inertial set of motion where there is rotation, acceleration, etc. And there's a misconception even among physicists that Einstein's theory of relativity, special relativity, is not applicable to situations of non-inertial motion. Anyway, that kind of a objection was raised about Sanac experiment. Therefore, Sanac's works went into oblivion. People ignored it. However, this is the point I make in my papers and so on. I solved this problem. I just solved this problem. What I wanted was, so I had to solve a dual problem. One is the synchronization of clocks, which people like Michaelson and Sanac had already solved by looping around. I also had to solve this problem of inertial motion versus non-inertial motion. I needed an experiment where the reference frame is moving inertially and the clocks are synchronized automatically. So I found a configuration which is not a rotating configuration. It's a stadium kind of a loop path. It's a different kind of configuration where the reference frame, the clocks, the detector, the emitter, everything is moving linearly, but the light goes around in a loop path and comes back. And I could do this kind of an experiment in the laboratory, and the results show that the relative velocity is exactly like the relative velocity of sound. It depends on the motion of the observer. It's a variable quantity.
All right, so I think that we should unpack the material solutions to this problem, or perhaps start to consider Ernst Mach's ideas.
Yes.
Do you want to take a very short break just to stretch really quick before we
Yes.
tackle that issue? Let's do that. I think
Yes.
it's always good to think about this for a minute and then come back to it. So
Okay.
During the break, I took a moment to read the Michaelson paper from 1925, the one that he did with Gale. Oops, I can't hear you
Yes.
for some reason. Oh, there we go. So you make the case that Sagnac does this experiment. There's reasons to dismiss it because of the design. But it seems like it would be difficult to also dismiss Michelson's experiment. And
Yes,
yet
right. Also. And Michelson was a more prominent figure. He was a leader. He was a Nobel laureate. But see, 1925, as I said, by then the theory, Einstein's theory was very well accepted. There were very few critics. There were critics always, but there were so few that I think the Michelson-Gale experiment it went unnoticed. That's what I think. But it's difficult to gauge. When I give talks on relativity and various things, I see that nobody has heard about the Michelson-Gale experiment except some senior people from a different generation. So anyway, so it's not very clear to me why it is so, but because it's very clear what Michelson says in that abstract is very clear. Referring to his 1904 paper, he says that when there is, if the ether is there, this is the kind of signal which is expected. And in 1925 writes that the expected signal is measured. It is seen in the experiment. And it's very clear. But he was also very, very careful. He says that this is consistent with Einstein's formulation. In a way, it is not exactly. It's actually very subtle, and to explain it will take some effort. But the point is, even today, you see, Sagnac's discovery was very important in terms of practical application. It's a Sagnac interferometer which is used today to measure what's called a gyroscope, to measure rotations in aeroplanes and so on. If you are in an aircraft, if you want to measure how its direction is changing, you need a gyroscope. What is used today is a laser-based gyroscope, active laser gyroscope, or a fiber laser gyroscope. All this based on Sagnac's idea that if you are in a rotating situation, light takes more time to travel the distance, and that can be measured, and that is a measure of rotation. So everywhere Sagnac gyro is very important in practical applications. However, nobody realizes that this was originally proposed as evidence for the existence of the ether. Okay. But Michelson experiment is, since it was looking at the rotation of the Earth, it is not that well known as the Sanac experiment.
Let's talk a little bit about how we could interpret all of this data in a slightly different light by considering the fact that there's an invalid assumption about empty space baked into all of this. And that if we start to consider that the universe is filled with matter that's all exerting gravity upon one another, we can reframe some of these results.
Yes, we should get to that. But before that, I thought there is one more point related to what you asked earlier, where Henri Bergson comes into picture. See, that is a question of what is called the concept of simultaneity. When do we say two events are simultaneous? Of course, if two events happen at our own location, we are sitting in some location in space. If some two events occur in the same location, we don't have any ambiguity about whether they are simultaneous or not simultaneous. But if these two events happen at a distance from us, at two different points, then some signal has to bring in this information about these events to us. How do we decide whether these two events are simultaneous or not? It's an important problem in physics. It's an important problem in general life, and it's an important problem of philosophy as well. So Bergson was an expert on issues related to time, duration, simultaneity, and he had certain philosophical views on it, maybe prejudices or views along the direction of thinking about absolute time, absolute simultaneity, and so on. And it is in this context, in the early 1900s, philosophers came into contact with the relativity theories, theory, in which all these concepts were thrown away. Concept of simultaneity, concept of clocks, time, because the rate of clocks, since it depended on the motion of the clocks, moving clock went slow, moving clock was running slower, time dilation. So for every observer, there was his own time, multitude of times. This was not really palatable to philosophers at that time, because philosophers thought there is one universal time, there's one universal concept of simultaneity. So people like Bergson got very interested in studying relativity theory, and they did study it very carefully. It is in this context, if you look at Einstein's writing, both his paper in 1905 and he wrote a popular book in 1960. It's called Relativity, the Special and General Theory. It's almost written for a popular, common man. That kind of it starts from very basic concepts about time, space, clocks, coordinate systems, and so on. Now there is a long discussion about simultaneity in this book, which is described in the context of a moving train. There's a platform. So one is talking about the relativity between the person on the platform and the person in the moving train. So in 1922, when Einstein visited Paris, there was one discussion session of discussions arranged by the Philosophical Society there. This was a session in Sorbonne, and Bergson happened to be there. Bergson was a very prominent most popular philosopher at that time. He was his lectures were very popular in Paris, and in that session, he was just one of the person who came to listen to what Einstein had to say. At some stage, there were some discussions, very short discussions, and in which Bergson was asked to comment on Einstein's theory because people knew that Bergson had studied these theories. And Bergson said, in this short time, he has studied it. He studied it for his own benefit, and it's a very interesting theory. But in a short discussion, he cannot express all that he thinks about this theory. However, he wanted to point out something about this concept of simultaneity in Einstein's theory. And he made short comments for a few minutes in which he said he indicated, he didn't explain it, but he indicated there is some real problem, the way Einstein deals with simultaneity in relativity theory. Einstein did not take it very seriously. However, in the same year, Bergson wrote a book which is called Duration and Simultaneity, written in French, published in 1922, in which he explains with extreme clarity where Einstein had gone wrong, real wrong, in dealing with simultaneity in relativity. Okay, so I didn't want to explain the whole writing here, but it's if Einstein had paid attention to what Bergson had to say in that book, Einstein himself would have been able to correct his theory, because what he talks about simultaneity in his theory is actually a blunder. Blunder in the sense, once you assume that the velocity, relative velocity of light is the same for everybody. Suppose you say relative velocity of light is invariant and the same for everybody, then the concept of simultaneity, which follows from that postulate, is in direct conflict with our experience, what we experience as simultaneity. Not as a common, I'm not talking about mathematical subtleties of relativity. We can experience directly in real life certain examples of simultaneity, and we know what the result is. The concept of the postulate of the invariant velocity of light is inconsistent with our experience of simultaneity. This was pointed out.
What are the examples that Bergson uses of simultaneity that is experienced?
So he analyzes the same example what Einstein describes in his book of the strain and the platform. So the example which Einstein uses is very, very simple. He says there's a train moving along a platform. The platform has endpoints A and B. Train has endpoints A prime and B prime. Now, let's assume that when the train reaches the platform, these points coincide, a point on the platform coinciding with a point on the train, and the second point on the platform coinciding with the second point on the train. Let's assume that there is an observer on the platform, there's an observer on the train at the midpoints, midpoint of platform, midpoint of the train. And they are coinciding at some point of time. They are in line with each other. Let's assume that at that time, 2 strokes of lightning happened at the 2 ends of the train. Somehow, so on end A and end B, 2 strokes of lightning has happened. light from this strokes of lightning will reach both observers. Now, since the person on the platform is at the midpoint, if he gets this light flashes from this two strokes of lightning at the same time in his clock, he will say the lighting happened simultaneously at the 2 points. See, because he is at the midpoint. Now the question Einstein asks is, for the observer in the train, are the two strokes simultaneous or not? He is moving relative to, but at this particular point when the strokes happened, the two observers coincided. And then there is analysis of what would the person inside the train conclude about simultaneity. That's the only question which is answered by both Einstein and Bergson. And the correct experience, if you think about it, the person in the train will not see it simultaneously because he is moving away. By the time the lightnings come from both sides, he would have moved away from the midpoint. Therefore, he cannot see this two strokes of lightning simultaneously. And that's our experience also. However, if the relative velocity is same for the observer on the platform and the observer on the train, suppose it is same, then their experience also has to be exactly same. When you analyze this, suppose a person on the platform sees this, how will we argue? He is on the midpoint. Light from the left side and the light from the right side are coming at the same relative velocity. So therefore, since I am in the midpoint, they will reach at the same time. So therefore, it's all simultaneous. Now the person in the train, how will he argue? He will say, when I was in the midpoint, the lighting happened. But the velocity of light does not depend on the velocity of the source. Okay. If the relative velocity of light from the left side and from the right side are exactly the same for the person on the train as well, then both pulses have to reach him also at the same time. There is no escape from that conclusion. So experience contradicts the postulate very clearly. However, Einstein, in his book as well as in his paper, when he argues about simultaneity, he forgets the fact that he has already assumed that the relative velocity of light is an invariant constant. He ignores that. He makes a blunder, really. And this blunder, Bergson points out very clearly in his book as one paragraph. One paragraph. But nobody took Bergson seriously at that time. It's a real blunder. Now, there is a direct consequence of all this. You know, GPS, all this only information, the way GPS works, the only information which comes from these satellites to our receiver in our mobile phone and so on are timing signals. The time at a satellite is at about 20,000 kilometers away. A timing signal comes saying that my position is this and I am sending the signal. This is the time in this atomic clock. And similar timing signals are coming from multiple satellites. To localize somebody in position in space, you need to convert these timing signals to distances. So there is a time of emission of the signal. There's a time of the arrival of the signal in the receiver. The difference is the duration. This duration has to be converted to a distance. Now, we know that the relative velocity does not depend on the velocity of the source. So the fact that the satellites are moving doesn't matter. It will only contribute to some Doppler shift in the frequency of signal, but not in the time, because relative velocity does not depend on the velocity of the source. Now the question is, in Einstein's theory, the relative velocity does not depend on the velocity of the observer also, the receiver also as well. Therefore, the distance conversion from duration to distance is a simple formula: invariant velocity multiplied by the duration. Distance is just invariant constant velocity c multiplied by the duration. So when we have three such durations, we can localize a person, a receiver. Okay. So it's a question of something like simultaneity. From three different satellites, which is a point where things are simultaneously localized. However, suppose this concept of Einstein's concept of postulate of invariant velocity is conflict with the concept of simultaneity. Then Einstein's formula cannot be used in actual practice of GPS operation. You need to use a formula which is used in a Galilean theory, like a relative velocity of sound. Because if the receiver is moving away from the satellite, you have to say c minus v. If the receiver is moving towards a satellite, you have to say c plus v and so on. Now it turns out the actual formula, the formula which is actually used in GPS, you can ask any expert in GPS, you will say it is not Einstein's formula. It is not c times duration to calculate the distance. It is c minus v times the duration. Okay. But that's a detail. What I'm saying is what Bergson said in 1922. It has its resonance echoing today in GPS operation. And all this has to do with the fact that the relative velocity is not an invariant constant.
The GPS example is an elegant proof of the way that a mathematical theory is perhaps elegant and beloved, but in practice is not used. And I think that that's the core of the argument here, which is that there are inconsistencies with the way that we mathematically apply these rules to reality, which is that we like the ideas behind relativity, but when push comes to shove and we have to design a system, we use different mathematics, and those mathematics seem to imply that the velocity is not constant, that the motion is affecting the perceived velocity.
Well, not the mathematics. What I mean is experience. Experience is what contradicts the postulate, the basic postulate of a special theory of relativity. Mm-hmm. See, if you look at Einstein's theory of relativity, that's the basis of all physics today. So one cannot say that everything what is said in the theory is incorrect, because most of the things had to be working in practice to say that the theory was successful, which is a fact. For example, various particle physics experiments and so on. See, if you really look at the theories of relativity, there are two vital physical effects which you actually see in phenomena. One is the fact that moving clocks run slowly, time dilation. In fact, that's the most important physical effects coming from theory of relativity. But this is a common effect. This effect is there in both kind of theories. It was there in the Lorenz's theory with ether. It's there in Einstein's theory without ether. So there are several physical effects which are described correctly in both theories, and they're all seen in actual empirical situations. But really crucial when you test a theory in physics, especially, there is a concept of what's called a crucial experiment. Even one experiment going against the theory will invalidate the theory. You don't have to test a whole lot of things. Even if 99 experiments are favoring the theory, if one experiment goes against that theory, then the whole theory can get replaced. Okay. In fact, there's a particular quotation from Einstein, which I would like to read out, which may be interesting. He says, the theoretical scientific researcher is not to be envied because nature, or more precisely put, experiment, is a merciless and not very kindly judge of his efforts. She never says yes to a theory. In the best case, merely perhaps, but in most cases, simply no. If an experiment agrees with the theory, it means perhaps. If it does not agree, then it means no. If every theory is sure to experience its no someday, most theories already do so soon after their formulation. So, this crucial experiments, that is a critical element here. If one experiment, even one experiment going against a theory, invalidates a theory. And here we have many examples of experience where the postulate seems to go against experience. Okay. So that is why, so therefore, there must be an alternate theory where these things are consistent. And that is what we should discuss. What is that consistent theory, which will explain everything which we know in empirical situation, and also consistent with the fact that light can propagate with a variable velocity.
Yeah, I mean, I think so. I assume that this leads us neatly to Mach and the involvement of the rest of the universe.
Yes, that's right. Now, one point.
Can I say one thing though? I love that Einstein quote. I haven't heard that one before, but one thing I love about it is that Einstein captures the essence of science, which is that it whittles down possibilities, right? Nature never says yes to your theory.
Yes.
It can only say, maybe, right?
Maybe, yes.
And people get so married to their theories because they think they're yeses. And I just love the humility in that Einstein quote of just recognizing that these theories all get chopped down and replaced eventually because new data becomes available, new ways of looking at things appear in people's imaginations. I just think that's underlining the possibility nature of theories. We permit these ideas into the sphere of possibility when they become theories, especially when they're widely accepted theories. They pass lots of different tests, but that doesn't mean that they are necessarily so. It just means they haven't been proven to be not so. That's really, really remarkable.
Yeah, he wrote it in 1912 in a paper which he wrote about superconductivity. Superconductivity was discovered in 1911. In 1912, he wrote a theoretical paper, and I think he was aware that he could be wrong about what he was saying. That is where he has his quotation. Of course, looking at judging from Einstein's personality, I wonder he ever thought his theory of relativity would be subject to the same fate someday.
I would assume so from the tone of that statement.
Okay.
I do like that about him a lot. All right, yes. So let's talk about Mach. Let's talk about the cause of these discrepancies and what you think the solution set looks like.
I actually have before we get there, I've been rolling this thing around in my head about the Michaelson-Gale experiment.
Yeah.
So is it possible to do this sort of experiment on a larger scale with experimental apparatuses that are already in place? Because you look at the Michaelson-Gale paper, and they spent a ton of money. They had an army engineer who helped them design this massive, kilometer-long path. Is there some place where this experiment could be repeated in the modern day without having to invest?
Yeah, I know it is always investment. If it costed at that time, it will cost much more today. However, You see, the Michelson-Gale experiment, the interferometer was already a size of a kilometer size interferometer. There was some mild vacuum and so on, based on whatever technology was available then. But today, the gravitational wave detectors are also Michelson interferometers, standard Michelson interferometers. Now, the next generation gravitational detectors, which are supposed to come up after about 10 years, they are sort of triangular configuration. Okay, in some sense, one can get similar data, Michelson data similar to what Michelson and Gale got in their rectangular interferometers in this closed triangular detectors of next generation. So it is not very difficult to do this kind of experiment with today's technology. You don't even need 1 kilometer size with today's technology, because when Michelson did these experiments, there was no laser. Laser was discovered after 1960. So Michelson was doing all these experiments using discharge lamps and things like that. Very, very small amount of light. But today, the same experiments can be done with much more sensitivity on even a smaller scale. Okay, with good vacuum. And so doing the experiment is not a problem. What is the problem? The problem is in convincing people that here there is something to be explained. And it's very difficult to convince people that there is a deviation which doesn't agree with Einstein's postulate.
But doesn't the GPS make it apparent?
Well, they just discount it based on the non-inertial business that we talked about.
Yeah, most of the time that's what they do. See, even there is an issue. See, GPS was a technology which was implemented not by physics people. It was implemented by defense people. Okay, military and all that. So there were physicists and engineers working in that, but mostly engineers. The physics people who were working in that tried to use, and they knew about the effects of relativity. And when the first two satellites which were sent up in the GPS constellation, of course, now there are many such constellations, but when the first satellites went up, they assumed that Einstein's formulae based on Einstein's special theory of relativity would be sufficient, apart from the gravitational effect on two clocks and so on. But soon they realized that those formulae did not work. So there were post facto corrections introduced in the GPS algorithms. And one of them is this correction using C minus V and C plus V instead of C. Instead of using a constant velocity, you use a variable velocity. But the justification given by GPS physicists, main person name is Neil Ashby. He writes a lot on this, Neil Ashby. The main logical basis he talks about is about this non-inertial motion and things like that. Same objections which was raised again about Sarnak's experiment, people now write about GPS as well. But they are not sufficient, I would say. I will give you one example, which is very interesting example. Suppose you see a flock of birds flying backwards, carrying a clock. So there's a flock of birds, they carry a clock, but they're flying backwards. You, of course, immediately know, any common sense person will know that birds cannot fly backwards with flapping their wings. The only way this can happen is when our observer himself is moving faster than the birds in the same direction, we have the illusion that the birds are flying backwards. Now you ask the question, whether clocks carried by these birds, will it go faster and slower or slower? Will it have a time dilation? Einstein's theory says yes, because the clock is moving relatively. The clock is moving relatively, therefore it should go slower. But I know from common sense that I must be moving faster than the birds. That is why birds are flying backwards. Therefore, the clock carried by me should be going slower. Okay. It is just a common sense objection. It is not a evidence against Einstein's theory. I'm not presenting it as a evidence. But I already see common sense of even an uneducated man can conflict with the best theories of physics. And one should take this common sense conflicts very seriously and think about it. Sometimes it may be irrelevant, but sometimes it can be very relevant. Okay, now we can get back to Mach and
Yeah, what's actually going on in your opinion?
What's actually?
Yeah, what's the hidden story here? So
There's
these problems, there's some contradictions. Yeah. What does the solution set look like?
Yes. Now we come back to this issue of cosmology. We know very well that these theories were formulated, perfected, and so on before we knew about the extent of the cosmos, the amount of matter in the cosmos, and so on. So after 1930, after Edwin Hubble's observation that there are a lot of extragalactic objects which seems to be going away from us at a velocity proportional to their distance, people started looking at galaxies outside, far away, using the new generation of large telescopes, 1 meter telescope, Palomar, and various other places. Then slowly, we realized that the universe was at least 1,000 times larger than what we thought it is. Okay, we knew this Milky Way and a few nebulae around this Magellanic clouds and so on. But with these new telescopes, we realized that the universe is at least 1,000 times larger. If it is 1,000 times larger, of course, the volume is 1 billion times larger, cube of this 1,000. So if the volume is 1 billion times larger, we also expect the matter in this universe also 1 billion times larger than what we thought it was. All that is fine. But now, if there is so much matter, there has to be corresponding amount of gravity. And gravity is a very special interaction because it can affect clocks, it can affect propagation of objects, it can affect all dynamics. Even Einstein's theory itself, the general theory of relativity, which is a theory of gravity, also says these things. We already know from experiments that if you have two clocks at two different gravitational potentials, one at a lower potential, another at a higher distance, a different potential, these two clocks will run at different rates depending on the value of the potential at the location of the clocks. So there is gravitational time dilation. And there is a difference in gravitational potential. It can affect the rate at which the clock runs. However, such effects are not included in the present theories, in the sense, with this enormous gravity in this universe, with this enormous gravitational potentials, if there is any effect on clocks and propagation of light and so on, those effects are not part of our current theories, because in the current theories, matter in the universe is not even considered. So there is a very big missing factor. Of course, we don't know a priori that this gravity has a significant effect or not. That we have to calculate. But the fact that gravity affects everything means we need to reconsider our theories. That because we have this new information about the universe, and if the gravity has any importance, if its magnitude is sufficient to affect phenomena in the laboratory, we have to reconsider these theories and calculate all these effects and see whether this is significant to change the theories or not. That's the basic premise. Now this calculation can be done, and some very interesting facts come out when you do even a rough calculation. See, today cosmology has developed to a stage where we have a reasonably good idea about the average density of matter and energy in the universe. Okay. So we have direct observation of galaxies and various sources which emits light. But that is not all the matter. There is what is called dark matter, for example. They are indirectly measured using their gravitational effects. So we have some measurements of this average density of the universe. There is some uncertainty, both conceptual and quantitative uncertainty in all these measurements. But we have a reasonable idea how much matter is there, how much energy is there, and so on in the universe today. If you use these observational values and calculate the total gravitational potential in our rooms, for example, in your room or in the room I am sitting, the same value, because the universe has the same kind of appearance relative to our small Earth. The number which comes out is a very interesting number. The total gravitational potential due to all the matter in the universe, all the matter and energy in the universe, if you calculate, you get a number which is numerically very close to the square of the velocity of light. That's velocity of light is 300,000 kilometers per second. Take the square of that. That's a number. That number matches the value of the total gravitational potential of all the matter and energy in the universe. So this is not a coincidence. There is something profound in the fact that these two numbers match. First suggestion is the propagation of light is controlled by the gravity of the matter in the universe. That is why there is a relation between the velocity of light and the gravitational potential of all the matter and energy in the universe. The cosmic gravity, its value, is equal to the square of the velocity of light. Okay. So not only that it is enormous gravity, it's also this particular value I talked about. This can be calculated. This fact was known for a long time. People did not connect it up with anything else, but this fact was known for a long time. It's not a new fact. That is one thing. Now, referring back to Mach's principle. See, what Mach said was very profound. Everybody agrees that what Mach said and what is called Mach's principle today, it was named Mach's principle by Einstein himself. Even Einstein said it's a very profound principle. But you all know that Mach's principle is not part of our standard physics today. Mach's principle is talked about as an extraneous principle. It is not part of any standard theories of physics today. There's a reason for that, which when I first realized this, I was really amazed. Mach's principle implies that there is one universal frame, one universe. Because Mach's principle says uh, effects of dynamics, centrifugal force and things like that, happens because of some interaction with the rest of the matter in the universe. Whatever that interaction is, since universe is one reference frame, accepting Mach's principle immediately implies accepting a absolute frame like ether and so on. But once you accept a absolute frame, the direct consequence is that propagation of light is Galilean. The relative velocity of light will depend on the velocity of the observer. So Mach's principle cannot be incorporated in current physics without breaking Einstein's theory, without throwing away Einstein's theory of relativity. So because of this, though Einstein really, if you look at the history of the development of general theory of relativity, how Einstein developed that theory, for about 5 years, Einstein could not decide whether Mach's principle should be taken as a basis of general theory of relativity or some other principle. He tried incorporating Mach's principle into his theory of gravity, the general theory of relativity. He could not, because general theory of relativity was based on special theory of relativity, in which he already assumed the invariance of the velocity of light. But Mach's principle needs an absolute frame, which will deny the basic postulate of special theory of relativity. Therefore, he finally discarded Mach's principle. That is why Mach's principle is not anymore discussed in physics. So anyway, so the interaction, gravitational interaction with all the matter in the universe provides this gravitational potential affecting everything in the universe. So if you take two clocks, one clock which is stationary in this universe and another clock which is moving in this universe, the gravitational potential experienced by the moving clock is slightly different from gravitational potential experienced by the stationary clock. And this can be calculated. Since you know what is the gravitational potential for a stationary frame, which is, I said, the square of the velocity of light, you can very precisely calculate what is the gravitational potential felt by a clock which is moving. And then it turns out that the time dilation which we see, muons and accelerators and so on, or moving real clocks in the laboratory, all the time dilations which we see experimentally matches exactly with the gravitational effect of the universe. So therefore, we have an explanation for phenomena like time dilation, which is a prime effect of relativity we see in the laboratory. Laboratory evidence for relativity is prime example is time dilation. We know that you don't need Einstein's theory to explain that. We need only the gravity of the universe. Similarly, for many physical effects in the laboratory, we can do this calculation. The effect of the gravity of the cosmic matter on what we see in the laboratory. And for every instance, without any exception, it matches. The calculation matches what we see in the laboratory. So every relativistic effect which we see in the laboratory today can be explained as a consequence of the gravity of the matter in the universe.
I mean, that's a very, very profound framing of the interrelation of the cosmos and the effect that the distant stars have upon us. It's a formulation that's been around since Mach's time, which he was writing in the 1920s?
I think late 1800s.
Yeah, 1870, 1880, those.
Right, because Einstein was familiar with it. And so
Yes.
it fell out of favor because relativity offers these very tantalizing thought experiments and purports to put us into personally, I think a more fantastical universe.
Yes.
And so now we're up against the challenge where you have two theories where the mathematics they can describe the same observed phenomenon.
Here the mathematics is different.
The mathematics is different, but the end point is that you have an observation, and you can
Yes.
use one set of mathematics, which is Einsteinian relativity, to describe it, and then you have another set of mathematics which refers to the cosmos to describe it, but
Yes.
the observation is the same. And so
Yeah.
this comes down to preference and belief, really. Like, this is a cultural
No, here
state
there
of
is no
affairs.
choice. Here there is no choice.
Okay,
I'll give you
explain.
Yes, okay. Because we can see the objects in the universe with a telescope or various measurements related. So there are galaxies and so on. They are really there. They are not an illusion. If those objects are there has to be gravity of corresponding those objects. There's no choice, right? So if gravity is there, those gravitational effects would be there. So now, if suppose Einstein's theory is right, then you will have double the effects. One due to Einstein's formulation, whatever that is, and this gravitational effect which has to be there because those objects are really there. But you cannot have both together because that will have double the effect. So you have to make a choice between between the two. And the choice is obvious because those objects are there. You cannot choose Einstein's theory and say, though those objects are there, their gravity is not real. You cannot make such fun.
I love that it simplifies things and speaks in terms of the real material objects. But gravity itself is still a nightmare, right? So why do two atoms attract to one another at the end of the day? Do you spend any time thinking about that at a material scale? Like, what are the atoms actually doing to pull each other together?
Yes, you can ask the same question about electrical forces as well.
Of course.
Okay, so why matter interacts with matter in this particular way is a deeper question. I would say it's a deeper question.
Right.
So, for example, take the concept of a field, gravitational field, magnetic field, and electric field.
Sure.
We cannot experience any of these fields. All we can see is when we put two pieces of matter together with certain properties, they either attract or repel. There's a force. We can push one with another.
Yeah, they're like maps of effects, essentially. They're like predictable maps of effects.
And because we like continuity, the concept of continuity, we don't like action at a distance. We like only when we see something being pushed, we want to associate something local pushing it. By postulating a field, we can say, okay, I have a piece of matter, which creates a field which is everywhere. Then that field acts on another piece of matter. It's a nice concept. But every field, whether it is gravitational, whether electric or magnetic, they are all unobservable entities in physics. Okay, they are postulated. They are what we would call free creations of our mind.
Right, they're abstractions.
We can never verify their reality the way we verify the reality of matter, solid matter. So there is a gradation of realities which we use in physics, but there's no escape from that using such concepts. That's the way we understand.
Do you think there's no escape, or do you think that we just haven't conceptualized it fully?
No, any other way of talking about this becomes very complicated. There is a formulation of interaction between two objects to matter, whether it is gravitation or electrodynamics. There's a formulation of action at a distance. There are mathematical formulations of how two objects interact without a field intervening these two objects. They are called action-at a distance theories, but they are mathematically very, formidable.
But the question is not necessarily whether or not there's not a field in between the two objects. The question is the field made of something?
Yes. So how do we decide that? No, that's a problem. So now, one thing which we seem to agree, even that is debatable, but seem to agree, is that this field contains energy. And when we are talking about just an attraction of two objects, it's not so obvious. But when we talk about a propagating wave, for example, you move an object, either a mass or a charge, it generates electromagnetic wave, which can transfer energy from here to there. Because we can do all this communication with the electromagnetic waves. So there seems to be some reason in proposing that there is a field which is independent of matter, which can propagate, which can affect, and so on. There seem to be reasonable concepts.
Again, it's not necessarily that there isn't the effects of the field. It's like when we talk about energy. Well, I think one of my favorite definitions for energy is material in motion, or material that can be, in the terms of potential energy, it's material that under other circumstances will go into motion. And so when we talk about energy in terms of electromagnetic waves, all of a sudden we kind of throw our hands up and we say, well, there's nothing in the field itself is in motion, but the field is mathematical. The field is a set of measurements that we have made.
Yeah. So this would have been a puzzle, but for the relation which Einstein himself clarified, equating energy and mass. So when he said there is equivalence between energy and mass, that in some way not solved, but at least reconcile this problem. That energy equivalence to some kind of a matter. So when you come to quantum theories, for example, we talk about photons, particles of light, instead of just waves. There, at least, we think of photon as some localized quanta of energy, very similar to matter, though it is not really as real as matter. But at least we talk about quanta of energy, very much like a particle. In that sense, there is a close analogy. I agree that they are not the same. They are not the same. It is not exactly matter in the normal sense, like an electron moving or a fundamental particle moving. But photon is treated as a fundamental particle with the properties of a particle today.
I guess the thing that leaves me deeply unsatisfied comes back to this human intuition, which is that if quantum fields, when you come down to the bottom of it, are pure energy, which is determined by the measurements made of, let's say, the 0-point energy of the vacuum, or inside of a particle collider, you have some...
Just momentum transfer, really.
Yeah, you have some kind of momentum transfer between the thing that you're measuring and your detector. Those things are not, in the current models, those things are not material. And yet, they produce material objects somehow.
Yes.
And there's this void where no one has yet figured out how to cross it, because you have, on one hand, pure energy, and then on the other hand, you have tangible matter.
And it seems like people stopped looking because of this Michaelson Morley experiment. They gave up on the static ether. And it seems very much impossible to explain these action at distances without the material objects being in contact with one another somehow to affect this momentum transfer.
And the field stands in for that object, right? We're like, look, there's a field in between them, so there's no action at a distance. Really, it's the field that's propagating these effects. But it's like, how does the field become a material?
Yeah, but if you look at the modern theoretical physics, it has gone even beyond this. In fact, something which even a practicing physicist like me find a bit strange, because field theories say that even particles are fields. Electrons, protons, and various things are actually fields.
But their
And
particular excitation of the
excitation,
underlying
yes,
field.
but that is only a theoretical formulation. These are just our own creations. This is all this kind of concept evolved out of mathematizing the theory further and further, so that people could explain everything in a unified some picture. That doesn't mean that what we created in our theories is what is there in real nature. But this is how we treat everything today as fields.
And what if instead of fields and instead of the static ether, we imagine that the atoms themselves obviously they have some surface that we consider as the atom, right? The shell of the electron or whatever it is for the chemist. But that there is some rarefied portion of the atom beyond that shell which connects them to their neighbors, which is imponderable, but is carried with the atom wherever it moves. Then you have a dynamical ether that's not actually static as a background. It can't be measured separately because it moves wherever the atoms move. And what if there's a structure there still? What if we don't have to give up on material explanations for these things?
Yeah, it's when you ask this question, I feel a bit strange. That's because of another reason. See, today we think of dynamics as consisting of matter, fields, motion, and those kind of concepts. However, there is a formulation of mechanics due to William Roman Hamilton's formulation, Hamiltonian mechanics. In the Hamiltonian mechanics, which came in the 1830s, the fundamental object there, entity, is what is called action. So there is a principle of least action or stationary action, where you say the path of dynamics, the actual path of dynamics, is a path where this quantity called action is minimized. Okay, and you can derive all dynamics, every aspect of dynamics, whether it's electrodynamics or any other kind of dynamics, from these action principles using Hamiltonian formulation. Now, if you think of this action, what is this action? Is it something like a field or something real? People have not spent much time thinking about it. It is still used as a mathematical convenience. However,
because action without actors is sort of nonsensical in our everyday conception.
However, if you think about action, you see this principle of least action works in real space and time. Okay, so you are saying there are various possible paths in space and time, and one of those paths or one set of those paths is chosen, cancelling all other paths possible. You know that a path cannot be cancelled with another path. The only way you can cancel something is when you have something like a wave, something which can go positive and negative. So there has to be something in real space and time with the properties of waves, so that you can cancel some paths and enhance some other paths. If you think that way, something like action has to be a real stuff in real space and time. Otherwise, how can action principle work? So the fact that action principle works in every instance of physical dynamics, whether it is standard particle mechanics or electrodynamics or gravity or any other field theory, everywhere action principle works. then you might say, okay, action might be something in real space. We cannot feel it. We cannot see it. We cannot experience, sense it. But if such a thing is there as a real entity, it is around every atom, every particle, and so on, as some real extended entity with the properties of a wave. So, though your question was not in this context, already we see that there is a possibility that there are things which we cannot feel, sense, and so on directly, but which could be really there in space and time around matter, which controls all dynamics.
Mm.
And this is
There's
the
a
greatest challenge of physics, I think, because
Yes,
physics
yes,
is unseen. Physics
yes,
is things that we have to spend so much time and effort designing detectors and measurement apparatuses in order to be able to feel something which we then have to translate to some mental theoretical model. And biology doesn't work in the same way. You can look through a microscope and you can see the
yes,
structures as they
yes,
go. And so it forces it to be physical. It forces it to be material. And physics just doesn't have that because it is so small and so undetectable that we are left with the limits of imagination.
yeah. But at the same time, physics has an advantage that things don't change. The same thing repeats every time you do. You create a situation, everything happens in the same way, not like a living matter. Things are not uh, changing. So therefore, uh, uh, a consistent picture can be obtained by persistently probing something the same way again and again. Earlier, you mentioned this question of energy of motion, kinetic energy that we understand. Something move and we call it kinetic energy. But you also mentioned potential energy. Now, when you say potential, electric potential, for example, we cannot see a potential. What we can see is only the variation of a potential in space, which we call a field. Electric field, when we say electric field, it's a variation of electric potential in space. For example, there are these demonstrations where we have a room which is electrically elevated to 1,000 volts. We can stand inside that room without getting a shock because it's a constant potential. But if we touch something with a different potential, we'll get a shock. So potential, which we use, it's a term which we use very often in physics, but we cannot sense a potential. We cannot see a potential. What we can sense is only a variation of the potential in space or a change of potential in time. A time variation of a potential we can detect as a field. We can also detect a spatial variation of a potential as a force, electrical force, and so on. So it's very much like this action in dynamics is very much like that. We cannot feel action, but the spatial variation of action is what we call momentum. In the Hamiltonian dynamics, the spatial variation of action is what we call momentum. Momentum, we have a sense of what momentum is. Also, the time variation of action is what we call energy in dynamics. So, but unless the action has a reality, we cannot have a spatial variation of action and a time dependence of action. So action must be real and is some extended object around every material body and so on, which controls all dynamics. So these are things which are still uh, unexplored sufficiently in physics. We know the mathematics. We know all the mathematical expressions related to this. But what's the physical reality of these things? We have not explored sufficiently.
And I would say, go ahead.
I think that's a perfect place to pause for now. I think that's a beautiful realization. I think it points to a huge conceptual body of work that has yet to come.
Yes.
Of
And
of explanation versus just description.
yes, description is easy. Description is easy because that is what we see in the laboratory phenomenon. When we see a lot of phenomena, we can say, we can describe it. We can even sort of give a plausible framework. But explaining something, starting from a small number of premises, without making a new premise for each explanation, that is where the power of theory, physical theory comes. And whether it is a consistent theory or not is again determined by these crucial experiments. So it's a back and forth interaction between sufficiently cleverly designed experiments and this imagination, free creations of our mind.
Mhm. I love that. I also, before we leave, I want to say how beautifully written your papers are. You know, oftentimes scientific papers are abstruse, especially about physics. They can be very complex and heavy in the language, but your prose is very clear, and the logic that the ideas follow is so beautifully laid out that it was a joy to read your papers. So thank you for that.
See the clarity. Clarity is the most important when you want to communicate. Okay, and that comes with only a wish. One has to have the desire to be clear. And the most clear expositions I have seen in my life is by Einstein. If you do read Einstein's writings, that clarity, and that's the kind of clarity one desires to achieve. Of course, his language is very fine and all that. Achieving that is difficult. But when I write a paper, I also try to ask people around me to see it and try to explain it to. I'm very keen that whatever I think of as a conceptual, even a deep thought in physics, I should be able to explain to a schoolboy.
I love that.
I should be able to explain forget schoolboy. I should be able to explain to my parents, my sister or brother or somebody, because they will ask me, what are you doing? I should be able to explain. And
That's such a huge motivation for our work as well. Like when we were in graduate school, we were both studying electrical phenomena, and we came up against this question of what is charge, and that doesn't have an explanation. It has a measurement, and that was what set us on this path where we're exploring physics and trying to find theories that can actually hold together for a full explanation, because you can't talk to people about these ideas if you can't explain them even to yourself.
Yeah. Because, finally, why are we doing all this? You see, when we try to make a theory or when we try to think of physics, why explanations in physics or any other science, that is for the whole community. It is not for just a personal. Of course, personal desire is the first thing which comes. You have a passion to understand. You want to understand, but that understanding is not just for yourself. Having understood, you want to talk about it to people around you, explain it, teach to students, and various things like that. So achieving a certain level of clarity is very important for me always.
It shines through.
Yeah,
I
you're doing a great
appreciate
job. Thank you so much, and thanks for taking the time to, get into some of these issues. I think that we have made more sense of, particularly a lot of these basic interferometer ideas that we've talked around in the show. I think that we've gotten a lot more clarity. So I thank you for that. By the way, before you go, if people want to find out more about you, is there a way for them to? What's the best place? Should they read your papers?
Okay.
Do you have a website, or how do you do this?
There is a Wikipedia page. There's a Wikipedia page with some information. I maintain a YouTube channel though I have not updated it for some time. I should do that with some of my talks and so on. Of course, I work in what is called a Defense Institute of Advanced Technology in Pune, in India. Earlier, I was in the Tata Institute of Fundamental Research. So I have a website, one of those Google site website. Again, it's not updated. I will update. But then 2 years ago, I wrote a book called New Relativity in the Gravitational Universe. It is published by Springer. So there is enough information on the web. When you do a web search, there is enough information about me in various places scattered, maybe. So that it's not difficult to find out more about me. And I always reply to emails and so on when people write to me. And,
Nice.
it was really a very nice experience talking to you both. I really enjoyed, just talking to you on various things, because this is what I will do when some of my friends come here and sit. We talk about various things, and I learn from them. They want to learn from me, and so on.
It's beautiful.
I
That's
really,
what we're going for.
Yeah, that's why we built this project, really, because it's hard to find those kind of friends. So we reach out across the internet to have these conversations. And
yes.
yeah, I'm really glad to have met you. I hope this isn't our last time meeting.
Yes. Yeah, some other time we can talk a bit about quantum mechanics, probably, because that is, conceptual issues. When you come to what one would call the unsolved conceptual issues, we always associate quantum physics with these unsolved conceptual issues. Today, I talked to you about this action and things like that. And it was not a random thought, because that's the kind of thing which I very passionately following up.
Excellent. Let's do that.
Yeah, that sounds perfect.
A couple months down the line, I think we have a
Yeah.
beautiful calendar right now. But
Yeah, please.
it's very, very, very reassuring to find people who are thinking along your lines. I feel like the world is a saner, more legible place for having you in it, and so thank you.
Yeah. Thank you very much.
Professor
Thank you.
Unnikrishnan. We'll see you again soon.
Yeah, have a great rest of your night. It's pretty late there, so
Thank you. Thank
good
you very
night,
much.
and take care.
Bye, everybody.
Bye.
Yeah. See you later.